do all the problems on the assignment that's due Monday. And then, as time allows, we'll get started on the next chapter where we will use kind of the basic structure of integers to help learn other techniques of writing proofs. So before we get started on that, are there any questions? Okay. On assignment 3? Oh yeah, okay, so f is a function from a to b, and b1 and b2 are subsets of b. So here's like the setup of what this function looks like, or what they're telling us. We have a set A. We have a function that sends elements of A into elements of B. We know that B1 and B2 are subsets over here in the B set, in the codomain. And what we want to do is we want to prove that if B1 is contained in B2, so in this little diagram, let's say if this is my B1 set, that if that is contained in this B2 set, if that's the case, we want to show that they're preimages, that the preimage of B1 is contained in the preimage of B2. So what we're hoping to show, and this I'm going to write in gray just because this is not a given, but if I kind of pull back and look at all the stuff that maps to B1, all the stuff in A that maps to B1, so that's the pullback or the preimage of B1, I want to show that that's got to be contained in the set of all the things that map into B2. So this over here, we have this containment, and we want to show this containment. So before I go any further, are there questions on just the setup, on the information that we're given and what it is we want to do here? Okay. So, I mean, it's an if-then proof, so I'm just going to start by supposing what they give us is true. So we'll suppose that B1 is contained in B2. And then I'm just going to write as a parenthetical, we will show that the pullback of B1 is contained in the pullback of B2. So if I want to show a containment, these containment proofs, we've done containment proofs before where we're trying to show that one set is contained in another set. And the way we do that is we just let X be a randomly selected element in the set on the left. So we could let X be an element of the preimage of B1. There's going to be a bunch of stuff here that happens. We're going to write some stuff, but at the end of it all, we want to be able to say then X is an element of the preimage of B2. What does it mean to be in the preimage of B1? What is the preimage of a set? Maybe we'll start there.
just from as set from the codomain?
Well, I guess I'm not really sure what you mean. Like, if X is in the preimage of B1, like, what does that mean? If, what we want to do is go back and, we're going to have to go back and look at the definitions, the new definitions of things. But it was one of the things we defined, I think, near the beginning, right here. So the preimage of a set F was all the domain elements in A that mapped into the set F in B. So if X is in the preimage of B1, what does that allow us to say?
That X would also be in the preimage of B2.
Well, I mean, that's what we want to get to, but we can't say that yet. We're just going to use the definition of preimage, using nothing more than what it means to be in the preimage, what the preimage is of a set.
It's in B?
Actually, no, it's definitely not going to be in B, because if it's in the preimage of B1, it's got to exist over here in A. So I'm just going to go back and look at this definition and an example we did. Here we had in part B, in this example, we have our set A was from -2 to 2, the integers -2 to 2. B was the set of integers from 0 to 5, and we had our function was x squared plus 1. So they said find the preimage of this set F. So this isn't all of B. They left out 1, but that's a subset of B. And they said let's find the preimage. So what we were looking for is all the elements of A that map to something in B, in F. So the preimage of F is here. Like, for example, are these elements. For example, -1 is in the preimage of F because F of -1 is 2, and that's an element of F. To be in the preimage, it means that if you send it through the function, you end up in that set. You're in the preimage of F because if I send that element through the function F, little f, it puts us in this set here. So if X is in the preimage of B1, what does that tell us? Can you turn on your mic?
B1. I don't know how to say it. So f of x is in B1?
Yeah, that's exactly what it tells us. It tells us nothing more than that. In fact, that's the only thing it tells us, is that f of x is an element of B1. Now we have an element over here. All right, we know that if I send x through the function, it puts us here. At some point, you're going to use our supposition that B1 is contained in B2. You're going to use the definition of a preimage again, but it takes maybe a couple, 2, 3 more lines to be able to deduce that X is going to be in the preimage of B2. Other questions?
Number 3 on the assignment.
Number 3. Yeah, so we have G mapping from A to B and F mapping from B to C. So that means F of G as a composition is defined. It maps from A to C. And we want to prove that if F and G are both injective, then their composition is injective. So I'll talk a little bit about exactly what we want to show and maybe like a general structure of how you want to do that. we're going to do kind of a similar problem at the end of this section that we're on, where we're actually going to show that if F and G are both surjective, then their composition is going to be surjective. And that might also kind of help just spur some ideas. But what do we have? G maps from A to B. F maps from B to C. So we know that their composition maps from A to C. So you're going to suppose G and F are both injective. You want to show that F of G is injective. So the way you show anything is injective, or the way I think a general approach to showing that a function is injective is that you suppose you have two inputs that map to the same out, and then you show that they must have been the same input to begin with. So oops. This one's G, this one's F. And then here we have F of G. So what you want to do is suppose, so F of G maps from A into C. So I want to suppose that I have two elements, maybe, you know, A1 and A2, so that if I send them through the composition F of G, they land at the same point. So we suppose that F of G of A1 is equal to F of G of A2. And you want to show that A1 is equal to A2. So, I mean, the first thing I might do is just rewrite these compositions in their other notation. So F of G of A1 is F of G of A1. And then over here, this is F of G of A2. You will use individually the properties that, you know, F is injective and then that G is injective. You get both of those. You're not going to use them both at the same time, but you'll use them in a particular order that allows you to draw some conclusions. And then we should be able to say that, you know, A1 is equal to A2. There's stuff to do there, right, that I've left out all the details, but that's the idea. That's the basic approach that you want to take with this one. Okay. Let's go ahead and pick up where we left off before. We were working with functions, and we had just made progress on one result, which is really, I guess, kind of a pair of results. So we started out, we have a function from A to B that's both one-to-one and onto, so injective and surjective. Then the inverse relation, F inverse, is a function that maps from B to A. That is also one-to-one and onto. That's the first thing. We'll look at the second part later. But we had just shown that that the F inverse, we know F inverse is a relation. We had shown that F inverse is in fact a function that maps from B to A. Because F is surjective, that means that the domain of F inverse is in fact all of B, and we showed that it was a function by using the fact that it was injective. So that was the first part, and then we want to show, well, that was the first part of the first part. Then for the other part of Roman numeral 1, we're going to show that F inverse is 1 to 1 and that F inverse is onto. So we can get started with that. Let's see. So item 2. We're going to show F inverse is 1 to 1. Well, we're going to do this, we're going to take the same approach that we usually take if we're showing that a function is 1 to 1. We're going to suppose we have a couple inputs that map to the same output, and then show that those inputs must have been the same in the first place. So F inverse maps from B to A. So I'm going to suppose that F inverse of B1 is equal to F inverse of B2 for elements B1 and B2 in the set B. We're going to show B1 is in fact equal to B2. So F inverse of B1, like F inverse maps from B into A. So F inverse of B1 is some element in A. Let's suppose these guys both map to an element, I'll just call it A. So let's say F inverse of B1 is equal to A, and F inverse of B2 also equal to A, right? We're supposing they have the same output. I'm just going to now go switch from using the inverse function to the function itself. If F inverse of B1 is equal to A, that means that F of A is equal to B1. And if F inverse of B2 is equal to A, that means that F of A is equal to B2. Oh, not B squared, B2. Now, what we know about F that's going to allow us to make the desired conclusion is that F is a function. It's not that F is 1 to 1 or surjective that helps us out here in this particular instance. It's that F is a function. And as a function, you can't split your outputs. A maps to a single element, and there can be no ambiguity about where the element A maps to if you plug it into a function. So because F is a function, B1 and B2 have to be equal to each other.
Is that like saying one element of the domain maps to one image?
It means, yeah, like, so with a function, a particular input can go to only one out. A function could double up on outs, like, to be a function, you could have two inputs mapped to the same output. It wouldn't be 1 to 1, but it would still be a function. You just can't have one input mapping to different outputs. That's not allowed in order to be a function. So this is enough for us to conclude that B1 is equal to B2, and that's what we wanted to show on this part. So that means F inverse is 1 to 1. My favorite example of a function and what should be allowed and what should not be allowed is like the snack machine where like you punch in the code like A3 or whatever and it gives you Doritos. Like there's absolutely nothing wrong with having 2 rows of Doritos. That would make that snack machine not 1 to 1 because I have 2 inputs, 2 codes that map to the same snack. But I can't have a single row that has like Doritos and Cheetos and Snickers because that would be chaos. When I punch in A3, I need to be really clear about what it's going to give me every single time, right? So we know that F inverse is 1 to 1, and now the last part of the first part of the proof is that we're going to show that it's onto. Okay, now, just as a reminder, F inverse maps from B into A. To show that it maps from B onto A, what we need to do is pick an arbitrary element of A and show that there must be some element in B that maps to it under F inverse, right? Everything in your codomain gets hit by the function. So let's let A be an element of A. And just to kind of state our intentions, we're going to show there is some element B of B such that F inverse of B is equal to A. Well, look, we have an element of A right now. We don't, our function F inverse maps from B into A. So if I had an element of B, I could just send it through the F inverse function, but I don't have that yet. What I have on my hands right now is an element of A. And if I have an element of A, the function that we have at our disposal is the F function. That's the function that maps from A to B. And the domain of F is all of A. So I know I could take that element A and send it into B. So let's do that. F of A is equal to, I'll just call it little b for some element B in the set B. In fact, maybe I'll call it B1 just to be kind of more particular. I don't want to use the same B that I talked about up here, but I know that F of A gets mapped to some element in B1, or in B, that we're calling B1. So look, if F of A is equal to B1, can I turn that equation around? What does it look like if we turn it around? Mm-hmm. So we found that element in B that maps to A under F inverse. It's this particular one that we called B1. That means that F inverse is onto. And that is the end of the first part of the proof. So if we know our function that goes from A to B is injective and surjective, then the inverse relation is in fact a function that is injective and surjective. The other part, I'm going to scroll up again just to review this part that we're going to start now. Conversely, given a function from A to B, f that maps from A to B, if f inverse is a function from B to A, like the domain is all of B and it maps into A, then f must be one-to-one and onto. So let's begin on that part. Let's suppose that f inverse from B to A is a function. We're going to show two things. One, we're going to show that the function f is one-to-one and that the function f is onto. So let's start with the first part. Show that f is one-to-one. How do we show that a function is one-to-one?
They yield the same answer, then one-to-one.
If what yields the same answer?
Function of an element in A,
Uh-huh.
an element in B.
Well, it's not that we can only apply f to elements of A, right? So f will map from A into B. How do we begin? Like usually we start with like one line. That's how we kind of get going on these one-to-one proofs. We're going to suppose something.
Since you can only map F to A, then you just choose 2 elements
Sure, like what?
in A.
Mhm.
You do A1 and A2.
Okay, so what are we going to do with those?
It should be pretty similar to what we did
Uh-huh.
in 2.
So if I have an element in A, what can we do with that element?
You say that it passing through F would be
Yeah.
equivalent to
Yeah.
what passing across.
Yeah, so we're going to suppose that f of A1 is equal to f of A2 for some elements A1 and A2 in A. So let's say maybe they both map to the same element. We'll call it little b, just to be creative. So I've got these 2 equations. What can we do with them?
We can say FB is A1.
We can say what?
F inverse
Uh-huh.
B is
Yeah.
A1.
Because we know that f inverse is a function, right, that maps from B into A. So we can turn this around to get the f inverse equation. F inverse of B is equal to A1, and f inverse of B is equal to A2. And again, we know that f inverse is a function. Right? It's not just a relation, it is in fact a function. So if f inverse sends this one element B to both A1 and A2, what does that mean about A1 and A2?
They're equal.
Yeah, and it's not because f inverse is like 1-to-1 or has some special property. The only reason is because f inverse is a function. So look, we said let's suppose f of A1 is equal to f of A2. That's what we did in the beginning up here. Then we were able to conclude that we must have A1 equal to A2, and that means that f is 1-to-1.
So I have a question.
Yes.
If we always, I'm just confused to the point where like we're setting it equal to B,
Mm-hmm.
both sides of it, the A1 and A2.
Mm-hmm.
What scenario would this be wrong then? Like I can't think of a scenario, if you're setting them equal to the same thing, then you just switch it. Would they always be equal?
Well, what's important here is that what we were supposing in the beginning was that f inverse is a function. That it wasn't just a relation, but it's a function. And when we're trying to show that a function is 1-to-1, we start out by assuming that we have found a couple of elements that map to the same output. That's what we do right here in this equation highlighted in yellow at the top. Suppose we found a couple elements that map to the same output. If f inverse weren't actually a function and it were just a relation, we wouldn't be able to conclude that A1 is equal to A2. Because for a relation, anything goes. There's like no restrictions. There's nothing wrong with having, A1 mapped, or to having B mapped to all the elements of A, right? Like that, there's no problem with that at all, if it's just a relation. But because it's a function, that's what allows us to say that A1 is equal to A2. We start out by saying, it's like a what if, like this is our what if. Let's just entertain this like a thought experiment for a moment and see what we can conclude if this were the case. And if, supposing that f of A1 is equal to f of A2 forces us, if this conclusion is forced, then that's when we get to say that the function must be 1-to-1. I don't know if I answered your question.
It makes a little more sense now.
Okay, it'll make the more you do, like, looking at some of those practice exercises and working on maybe some of the assignment problems, the more you do, the more you get used to it. Like showing something's 1-to-1 almost always takes on this kind of form. Sometimes there's other Sometimes there's another approach you can take if there's something special is true about your sets, but this is the generic approach. So we have one more thing to show. We showed that F was 1 to 1. We need to show that F is onto. And I think we have enough space here. So the reason that, this property that we call surjective, the reason we also call it onto is because you could think of the function as like covering the whole codomain. Everything gets hit. It doesn't just map into a set, it maps onto it. It covers everything. So F maps from A to B, right? And this is just a reminder that our F function is the one that maps from A into B. And I want to show that everything in the codomain, everything in B gets hit, that the function covers that whole set. So what we do, our generic approach for showing that a function is onto or surjective is we pick an arbitrary element of that codomain. So we're going to let B be an element of B. And we're going to show that there exists some element in A that maps to it. So some A in A such that F of A is equal to B. And when I'm writing proofs, there's a couple things I try to do. First of all, I try to keep my eye on the ball, like meaning what is the desired conclusion? Like for us, it's that we want to find that element A, or at least show that it exists. And two, what is it that I get to use? Like what do I have at my disposal? What we have, I'm going to scroll up just a little bit here, is right up here at the top. Suppose F inverse is a function. And when we write this, when we say suppose F inverse is a function, part of this statement here is that the domain is all of B, right? Because it maps from B into A. So if I have an element of B, since the domain of F inverse is all of B, once I have an element of B, I can throw it in F inverse. And it's a function, and I know it'll send me to an element in A.
So basically you use the same conclusion or the same information about F inverse to imply basically that it's a function.
Yeah. Yeah, and really that's all, like I'm invoking that F inverse is a function and that its domain is all of B in particular. So I know that F inverse of B is equal to some element, I'll just call it A1 in A. Sends me somewhere in A. Well, what can I do with this equation? F inverse of B equals A. What can we do from there? Yeah. Right, turn the equation around. If F inverse of B is equal to A1, then F of A1 is equal to B. So look, we found an element. There must be some element in A that we're calling A1 here that maps to the element B that we chose. And that means that F inverse, oh, sorry, hold on. That means that F is onto. Yeah, because we said at the beginning, we just said let B be in B. We picked nothing specific about that element, little b, except that it was some element in our codomain. So if it could be any arbitrary element, if it's true for that element B that we chose arbitrarily, it's got to be true for all the elements of B. So we're done. Yeah. Now we declare victory. We didn't even need, I think I allowed for a third page just in case we needed it. It looks like we don't need it, so that feels pretty good.
Got to the end of the second one
Yeah, we did. Yeah. There was a lot to show, though. I mean, each part, like there were 2 main results, and each of those 2 main results had like 2 or 3 parts each. So we showed a lot in these 2 pages. So a result about functions and their inverses. I mean, a function and its inverse annihilate each other. So if our function from a to b is both 1-to-1 and onto, and requiring both 1-to-1 and onto, requiring 1-to-1 means that the inverse function will exist. Requiring onto means that the inverse function, its domain will be all of b. So if your function is 1-to-1 and onto, then when a function meets its inverse, they annihilate each other. So if I find f inverse of b, which is some element of a, and then I send that through the f function, it's got to send me right back to b, right? Like if I have, here's a function f, its inverse, f inverse goes from b to a. This just says, look, if I take an element in b and I pull it back to a, so I find its preimage in a, and then I decide to apply like the f function again, it should send me right back to where I started. And it works going the other way too. If I start with an element in a and then I apply the f function, it sends me over there in b. If I then apply the f inverse, it's going to send me back to where I came from. A function and its inverse annihilate each other.
Just a sanity check. Onto implies that the domain of the inverse function is all of b.
If f is onto, then if the inverse exists, it will be all of b.
Right.
Being 1-to-1 is what makes the inverse function exist. So like if a function is 1-to-1 but not necessarily onto, then the inverse function will still exist, but the domain of the inverse might just be some smaller subset of b. Because if not everything gets hit by the f function, then we can't pull it back necessarily. So here's a fun little exercise example that'll feel less abstract and more concrete. So kind of get our feet back on the ground here. We could find an inverse of a function. There's kind of a basic procedure here. One, the first thing I do is, just to make it convenient, is I write y for f of x, or some other variable, doesn't matter. Then I interchange the x and y's. So over in this example, I've got y equals 3x plus 6. If I'm interchanging x and y, I just have x equals 3y plus 6. I'm just kind of typographically swapping them. Next, solve for y. So this is a nice linear equation. Let's see, we get 3y equals x minus 6, and then we can divide by 3, so y is x minus 6 over 3. And then the last thing we do is write f inverse of x for y. And you could see for yourself, I mean, so f and f inverse both map from all reals to all reals. They're both linear functions. Keep in mind that when we found this linear function, when we were solving for y, all of our operations were 1-to-1 operations. Like none of them led to ambiguous answers. Like at no point did I need to take a square root of both sides. And remember, if we have to take a square root on both sides, we've got like plus or minus that we have to worry about. So nothing like that. And you could do a quick check here. If I find like f of f inverse of x, that's f of x minus 6 over 3. And the f function says first I'm going to multiply it by 3 and then add 6. So those cancel. And we do in fact get x. So there's an illustration of Theorem 112 above. Theorem 113 at the bottom of the page. So first, a definition, I guess. The identity function on any set is always the function that just leaves everything alone. So if we call the identity function I, then I of A is always equal to A. It doesn't move anything. That's the identity function. And Theorem 113 here just basically restates Theorem 112 above, that says, in Theorem 112 we kind of were working with a function from A to B and just said, oh, f of f inverse of B is equal to B. Like, it's just going to leave, if I compose a function with its inverse, it's just going to leave that element alone, right? Whatever, if I plug in B, I get B. If I do f inverse of f of A, I just get A. Like, it boils down to the identity function. And so this is just a restatement of, this part here is just a restatement of Theorem 112. Of Theorem 112, where the function f maps from a set to itself. And part A just says if I compose the identity function with any other function, it always just gives me that function f, which makes sense. Like, so in the first part here, right, that I composed with f says first apply f to your element. So f of A gives me some other element B. Then apply the identity. Then leave it alone, right, is what it says. So that's obviously the same thing as just applying f and doing nothing more. Okay, so we're going to finish this section by discussing a couple results and proving one of them. So in part A, we're going to prove this one below. Part B, this is on the assignment that you're turning in Monday. And part C just says, it follows directly from A and B. So if we have a function g that maps from A to B, I'm just going to sketch this out. So g maps from A to B, and f maps from B to C. We're going to suppose that G and F are both surjective, and we're going to show that their composition, f of G, is surjective. The composition mapping directly from A into C. So let's suppose that G and F are both surjective. We're going to show f of G is surjective. So to show that f of G is surjective, keep in mind f of G maps from A into C. We want to pick an element of our codomain, so we're going to pick an element of C. So let's let C be an element of C. I'm going to sketch that right up here. There's our element in C. We have that. I'm hoping, I'm going to put a little question mark by it because I can't say it yet, but I'm hoping there's an element over here in A that maps to it under f of G. I can't say that quite yet, but I do know that G and F are both surjective. So do this. First, let's use the fact that F is surjective. Keep in mind F maps from B into C. So I picked an element of C. Since F is surjective, what does that mean?
What about GB2?
I heard two people at once. Who wants to try again? Somebody must.
Would G also be surjective?
Well, G definitely is surjective. So we get that both, but we're only going to use the fact that F is surjective first. F maps from B into C, and we have grabbed an element of C, and because F is surjective, what does that tell us?
We can say that the inverse function of F has the domain of C.
Yeah, only we have to watch our language and what we assume. We don't know that F is injective, so we don't know that the inverse function exists. But what we do have, which is what I think you're getting at, is we know there's an element in B that will map to it. Right? So surjective is onto. So if F is onto, that means that when as F maps from B into C, it covers everything. Every element of C will get hit by some element of F. So
The B, right?
yeah, sorry. So every element of C will get hit by some element of B.
Okay. So if the inverse existed, it would also be true that the domain of that inverse would be the entirety of C.
Yes. Yes. And it would mean that there is only one element of B that map to it. Right? Now, all we know is that F is surjective, so there may be 2 elements or 3 elements of B that map to the element of C. That's fine. We just need to be able to grab one, and so that element exists. So here's what we've done so far. We've been able to pull this back to say, okay, I know that F of B is equal to C. I know that C gets mapped to by some element of B. So now look where we are. We're in B. Now use the fact that G is surjective. What does that tell us? Yeah, some element in A is going to map to the element B that we're looking at. We have this element B in the set B. G is surjective, so there's got to be something in the set A that maps to it. So oops. G of A is equal to B. So I'm going to kind of erase this question mark now and pull this back. What I know for sure is that this element A that we found maps to B under the F function. Now we're just going to pull these together. Our claim, here's our bold claim that will take us, all of a couple lines, I think, to establish. We found that element of A that maps to B. So my bold claim is that element of A will map right to C if I send it through the composition. So let's just show that. So F of G of A, which is F of G of A, I know what G of A is, right? That maps to B. So this is F of B, and F of B is equal to C. So we grabbed an arbitrary element of C. Oops. We grabbed an arbitrary element of C, and we found this element in A that maps to it under the composition, f of g. And that means that f of g is surjective. How's that? So in the problem that's on the homework, you're going to suppose that G and F are both injective functions individually and show that the composition f of g is injective. You're not going to do it by grabbing an arbitrary element of C and showing that something maps to it, because that's surjective. But what you can do is say, let's suppose that two elements of A, like f of g of A1, is equal to f of g of A2. You want to be able to show that those must have been the same elements of A1, and you'll use individually, one at a time, the fact that F is injective and the fact that G is injective, in whatever order kind of makes sense. It allows you to reach that desired conclusion. Questions before we move on? Okay. All right. So then let's take a look at chapter 2. In this chapter, we're starting out just by examining a couple other ways. You know, we are already, I think, pretty familiar with direct proof, and we're going to do another example. But, you know, when you prove something directly, when you prove an if-then, you just suppose the if statement's true, and you show that the then statement has to be true. That's a direct proof. We're going to use the structure of the integers to kind of help us learn a couple other techniques of proving things. Sometimes proving something directly is really hard, and it might be easier to kind of take a backdoor approach. So as we're writing proofs, sometimes there can be confusion about what can I assume that I know and what needs to be shown. You know, so I'm going to just start by stating a bunch of things that we get to assume are true, things that we already know and love about the integers. Axioms of equality, this is true for all sets, not just the integers. The axioms of equality are just that equals is an equivalence relation. Everything's equal to itself. If A is equal to B, then B is equal to A, and of course the transitive property. And then some properties specifically of the integers. So the integers are closed under addition and multiplication, meaning if I have two integers and I add them or multiply them, I'm just going to get another integer. I'm not going to like create a fraction or something from those operations. Addition and multiplication are commutative. Multiplication distributes over addition. We have the additive and multiplicative identities of 0 and 1 respectively. Every element has an additive inverse, so every integer has a negative. And there's a multiplication cancellation property. Integers don't have multiplicative inverses, not unless we build our set bigger and look into fractions, into the rationals. But we do have a cancellation property that simply says if AB is equal to AC, then B is equal to C, as long as A is not 0. And then the trichotomy axiom just says if you have an integer, it's either positive, 0, or negative. All of these, I think, are pretty clear. We've used these properties over and over again, even probably without stating them explicitly. So we'll look at different methods of proof. The direct proof, we've already seen some examples. That's what we've been relying on mostly. And we're going to do another one just to kind of drive that home. The other two are indirect methods. So the contrapositive, instead of proving A implies B, the contrapositive statement, which is logically equivalent, is if not B, then not A. So you switch the order and you negate each of them, each of the statements. And then proof by contradiction, which is one of my favorites, just says suppose that whatever you're trying to show isn't true, And if it weren't true, then the world would come crashing down around us. And since that's not happening, must be there was something wrong with my supposition in the first place. We're going to do an example of each. So here's a quick direct proof. Prove that if n is even, then n squared is even. So we're going to suppose that n is even. And, you know, these proofs were like even odd proofs, you know, like whether something's even or odd. Being even is equivalent to being able to say it's a multiple of 2, right? There's a factor of 2. So if n is even, then we know n is equal to 2k for some integer k. This part at the end, for some integer k, is really important because I can write 3 as 2k if k is 3 halves, right? So it's important that we have that statement that k is some integer. We want to show that n squared is even. So I have this equation involving n. We'll just square both sides. N squared is 2k squared. And if we square out 2k, we get 4k squared, a little algebra. And now I'm just going to drive it home. I want to, when I'm writing a proof, string the pearls for the reader. I want to make them work as little as possible. I want to make all the arguments I need to make. So I'm just going to rewrite this one more step. This is 2 times 2k squared. I want to be able to write it as 2 times some integer. That's what it means to be even. And then last, just make note that 2k squared has to be an integer because k is an integer. Then 2k squared is an integer. And I can just say that, right? Like this is part of those properties on the previous page that we know and love and we don't have to prove them. The integers are closed under multiplication. So if I multiply integers, I know I'm going to get an integer. And so n squared is even. Questions on that one? Okay. So we're going to do our next one is a proof by contrapositive, and this is just the converse of the last one. Now, it isn't always the case that if one statement is true, then its converse is true. The converse is what you get if you reverse the implication. So the converse of A implies B is B implies A. A lot of the time, you can't do that, right? In this case, you can. And we're going to prove this by contrapositive. So
did you say that a lot of the times you can't work from the fact that the contrapositive is also true?
a lot of the time the contrapositive isn't true for an if-then.
Okay.
Yep. So we will prove, and if I'm proving by contrapositive, I often just start by writing out what the contrapositive statement should be. So we will prove the following. So the contrapositive of if A, then B is if not B, then not A. So if n is not even, meaning if n is odd, then not A, then n squared is odd. That's the statement that we'll prove directly. And the reason that we want to use the contrapositive here, the reason that I would definitely not try to do this directly, or we would run into a brick wall immediately, is because if I try to prove it directly and I say, oh, let's suppose, I'll just do this on a different page. Let's suppose n squared is even. Then we can say n squared is 2k, right, for some integer k. Then I want to be able to conclude something about n, right? So how do I get to n? I have to take a square root? Then I don't even know if I'm in the integers anymore. Like, the integers are not closed under square roots. And that, like, I get nowhere. There's kind of no conclusions for me to draw. However, if I start with an assumption about n, I can get to n squared very easily, and I know I'm still an integer. So, let's suppose n is odd. The only thing we have to do is figure out what does that mean. I know if it's even, I can write it as 2k. But if it's odd, I'm just going to use the fact that the integers alternate between even and odd. So you're either an even, which means you're 2 times an integer, or you're odd, which means you're 1 more than some even integer, right? So we can write it as 2k plus 1. Some people like to use 2k minus 1 instead of 2k plus 1. Really, it's up to you. They're equivalent. Again, for some integer k. So let's observe the following. We can square both sides. Let's FOIL that out. We get 4k squared plus 4k plus 1. I'm getting kind of excited about that plus 1 on the end. I want to deduce that this is an odd number, right? So again, I want to complete the argument for the reader. I want to make them work as little as possible. So I'm going to make sure I can write that as 2 times something I know is an integer plus 1. So I'm just going to factor out a 2 from those first 2 terms. And then plus 1. And now at the end, I could say since k is an integer, what do I know about 2k squared plus 2k?
It's also an integer.
Yeah, because, and we don't have to prove this is on those properties on the last page, the integers are closed under multiplication and addition. So n squared is odd, as desired. Now, not everybody does this, but I kind of like to just go back and revisit what we wanted to show. This was an indirect proof. In this problem, they ask us to prove that if n squared is even, then n is even. Somehow our conclusion is, so n squared is odd, as desired. I like to just remind the reader now that we're done because this was the contrapositive.
Have you proven the contrapositive?
Yeah, having proven the contrapositive or by contrapositive, we have proven that if n squared is even, then n is even. Questions about this one?
I had a feeling that you were going to approach this one for the contradiction one.
Yeah, it's a classic. But unfortunately, we won't get to it today because it takes more than 7 minutes to do this next one. But this is a pretty famous result. We're going to show that the square root of 2 is irrational, and that's a nice one to do by contradiction. We'll do that on, today's Wednesday, I guess we'll do that on Monday. Until then, if you have questions on the assignment, just send me a message, an email or a Canvas message. Otherwise, I guess I'll see you all, and I'll be in Randolph on Monday.